Okay, so last class we were discussing this problem, right? So already you have solved up to, I think, C, D also you have solved, right? Only E part is remaining, the efficiency. So efficiency we know is P out by P in, right? So P out you know, output power, you don't know, right? So let us see how to do this. So this is what we have done last class. We found PO. PO is known, 240 kilowatt, right? And VT is 240 volt. And full load current we found 1000 ampere, right? And the induced EMF at full load will be VT plus IRA. So that will be nothing but 250 volt, right? Already you did this last class. And power developed will be EA, IA. So EA is 250 and IA is 1000. So you got 250 kilowatt, right? And omega m we can find because RPM is given 600 RPM. So we can convert it and we'll find it 20 pi radian per second, right? Then the torque developed, TD, we can find PD by omega m, right? So that will give me, already you have done this, 3978.87 Newton meter. Then the mechanical power input at full load will be PD plus PR, right? So that is 260 kilowatt. PR is given. And therefore the applied torque we can find out, that is P in by omega m. So P in is 260 kilowatt divided by 20 pi. So we'll find 4138.03 Newton meter. I hope everybody got this in the last class, right? So next we'll see this. This is a very important part where we'll find the efficiency, right? So in order to find the efficiency, we must know the losses. What are the losses happening? So in order to calculate the loss, we need to find the field current because we need to know the loss in the field circuit as well as the armature circuit, right? So in order to know the exact current in the field circuit, so what is the effective field current now at the full load is 2.5 ampere, right? Because you know the voltage, know the resistance, you just divide it, you'll find it 2.5 ampere. What is the voltage given? Can you tell me? Field voltage?
120 volt.
Huh?
120 volt.
120
And
volt.
resistance is
RF is?
RFW 30 ohm.
30 ohm. Okay. So from the magnetization curve, we need to find this.
Yeah.
So this is your magnetization curve. Okay. So how I'll find? Now we need to see the full load current. Sorry. The effective field current at full load is 2.5 ampere. So we'll see the voltage is given, VF is 120 volt, right? And NF is 500 turns. So NF, IF, we got how much? IF is, RF is given 30. So IF is 40 ampere, right? Not 40, 4 ampere. 4 ampere, right? So 4 ampere into NF. NF into IF, how much it is? So this is number of, so okay. So IF is 4 ampere, right? Just note it down. Then corresponding to 4 ampere, we'll see in the magnetization curve. So corresponding to the 4 ampere, 280 induced voltage, right? Induced EMF is 280. Okay. So so you got 2.5 ampere. 2.5 ampere. Sorry?
Does that 25% plays any role that the demagnetizing MMF due to arc reaction?
No, demagnetizing effect will consider later, but at full load we are getting NFIF. Okay, what is the EA we are getting at full load? That based on that we'll find. So EA we got at the full load, how much it is? 250 volt, right? So corresponding to the 250 volt, we can find the IF, right? So now corresponding to the 250 volt, this is your 250 volt here somewhere, right? So corresponding to this, so around 2.5, okay. So here we will get 2.5 ampere. So the effective field current at the full load will be 2.5 ampere, okay. And this will circulate in the field winding. So your effective MMF will be 500 into 2.5. That is 12. That is coming around 1250. Okay. Ampere turn per pole, right? Now, now the demagnetizing MMF due to the armature reaction is 25% of the full load current. Your full load current is 1000. So 25% of it is 250, right? Now the net MMF will be 1250 plus 250. So it will be around 1500 ampere turn per pole, right? Now for the 1500 ampere turn, we need to find again the IF. We know the number of turns is 500. So therefore, your IF will become 1500 by 500. So it will be 3 ampere. So corresponding to the 3 ampere, now your current, the net current in the field winding will be IF. That is 3 ampere, right? Now what will be the loss in the field circuit? VFIF, right? VFIF. Okay. So VF is given 120 volt, right? It is, here it is 120 volt into 3. So we'll get 360 watt, the power loss at field circuit, right? So now you can find the input power, right? So input power is whatever input power we got previously, that is power developed plus rotational loss. Rotational loss was 10 kilowatt and output power was 250 kilowatt. So both are added together, it is 260 kilowatt. Now if we'll add the copper loss in the field, so it will give me 260.36 kilowatt, right? Now I can find the efficiency. So efficiency will be how much? P in by P out, right? So how much is coming the efficiency? Can anybody tell? This is your efficiency. Which one? Okay. Is it visual now? Okay. So efficiency will get output power is 240 and input power is 260.36. So it is around 92.2%, right? Okay. Now part F is your total resistance in the variable resistance we need to find, RFX. Okay. So if we'll find the effective resistance RF, then I can subtract the resistance of the field winding, then I'll get the extra or external resistance connected to the field, right? So that means 120 by 3 will give me the effective resistance, right? So 3 ampere we got the field current and 120 volt is your voltage applied across the field. So your effective resistance is becoming 40 ohm, right? Like this is your field circuit. I'm just showing your field circuit here. This is your VF. Okay. Now this is your variable resistance RFX. Okay. And this is your RF. Okay. So now you can understood how to find RFX, right? RFX will be 40 minus 30, so 10 ohm, right? Okay. So this is okay. Another part is remaining G, that is voltage regulation. So voltage regulation you can found no load voltage minus full load voltage divided by full load voltage into 100, right? So it is coming around 10.83%. And it is also from the magnetization curve we have to find this no load voltage, right? Because field MMF is 1500, right? And so total net field MMF is 1500, and from the magnetization curve you can find the from here you can find the no load voltage, right? Okay. So 1500 for 3 ampere only you have to find. So here is the 3 ampere. 3 ampere is here, right? So you can just project it and you'll find it is around 266 volt. Okay. So therefore we can say here that graph paper you can take, accordingly you can do. Okay. If we'll be given the readings of open circuit test, you can plot it and you can do it, right? Okay. Suppose the readings are given of open circuit test, and you will use that and you'll plot the graph, and from the graph you'll do it, right? Okay. Okay. So this is about your separately excited DC generator. So today we'll see the Shunt generator. Okay. This is a self-excited generator. So self-excited generator, I told you, we have shunt connection, shunt connected and series connected, then compound connected, right? So first we'll talk about the shunt connection. So in the shunt connection, you can see here that the field winding is put across the armature, right? Here is the field winding and which is connected across the armature, right? So what this RA is represents? RA represents your armature resistance, which is actually the resistance of the armature winding and the brass contacts, both. Okay, there are certain resistance of brass contacts. So this resistance will represent the resistance of the armature winding as well as the brass contacts. Okay, and your NF is the number of turns in the field winding, and RFW is the resistance of the field winding, and RFX is your variable resistance connected in series with the field winding, right? And RL is your load. So now I'll say write the governing equation. How I will write? Under steady state, I can write the governing equation. I can write IA is equal to IF plus IL. Very good. Okay. Now if I'll write the equation of the generated EMF EA, that will be equal to how much it will be? EA will be, this is your VT, right? Terminal voltage. Okay, that is voltage across the load is the terminal voltage. Now I can write VT plus IARA. Okay. Any other equation you need to write in the field equation? If you write, what will be it? Field equation will be VT equal to RFW plus RFX into IF. Okay. So these are the three governing equations under steady state for the shunt connected generator. Okay. One is your VT equal to RFW. One more equation also we can write, that is VT equal to IL into RL, right? Okay. So these two equations are same, like equivalent, right? One is RFW plus RF into IF, right? So this is the VT, voltage across these two terminals is VT, okay, which is appearing across the load, right? Now the question is, when initially the shunt generator will start, suppose what is a generator? Generator means we are rotating the prime through the prime mover, the rotor of the generator, right? We are rotating it. Now there is no current in the field winding. How it will develop voltage? Initially there is no current, right? Now unless the voltage is developed in armature circuit, there will be no current in the field, right? So then how the initial voltage will be developed?
By weighing of this. By weighing of this.
But we don't have any supply to the field, right? How will vary the flux?
When you voltage is surplus because it's again and again. Then the
No, there is no voltage, right? Previously, no voltage is connected across the field winding. So now the question is how it will develop the voltage.
So I am saying it vary of flux.
How it will vary?
If you the area of contact with field changes, so it will vary of flux.
I am not getting what?
When the motor voltage it will vary the area of contact with the flux.
Vary the area of?
Contact.
Huh?
Area of contact is around vary करते तो फिर change होगा, right?
जो flux के साथ वो area of contact है उसको vary करें। क्योंकि जितनी लाइन में होगा जो flux को changes होगा उससे ये
Vary the, what is telling? Vary the area of contact. Which contact? No, slowly you tell, slowly I can get you, right?
Why equal to BA? What is in the work to why is in the work?
E equal to K phi P omega M, right? Okay. So now how will develop, you're telling?
And then pi equal to BA.
Pi equal to?
Pi. Flux is equal to flux density into area.
BA.
BA.
अच्छा BA, okay, okay.
So then the coil within the area of contact with the B.
Arey, this A is cross section area. It is constant. Okay.
And then B is very
B, how can you vary?
I'm not getting my point. I'm not getting my point.
Now B you cannot vary, right? Any other idea? I think his idea failed. Any other idea? अरे voltage है ही नहीं इधर. Now how it will develop? There will be no current through field winding, right? It is possible only if there is residual flux in the field. Unless there is residual flux in the field, it cannot develop voltage. Therefore, when we are connecting a machine in shunt fashion, shunt connected manner, before that we must energize the field winding before that around 1 or 2 hours, so that some residual flux must be in the field core. So that residual flux will help us in developing the voltage. How it will help? Suppose we have very small residual flux, let us say fire, right? Very small. And as soon as it is rotated, the generator is rotated through the prime mover, it will develop a small voltage across the armature. EA will be very small. Okay? So then, as EA will develop, then some current will flow through this. Under no load condition, if the load is not connected till that point, right? Okay, then some current will flow through the field, right? And that current again, it will excite more to produce more voltage. Gradually the voltage will step up, okay? And this phenomena we can see here in this picture very clearly. Okay, so now I can see here this ER. ER is the voltage generated in the armature because of the residual flux phi R. Okay, now what will happen with this ER? Certain current, if this is your resistance line of the field resistance line, already it is mentioned here, field resistance line. This is your field resistance line, right? So then, what will be the current now in the field circuit? It will be here. This is the current now, which will flow. Let us mark it as IF1. Okay? Now, corresponding to IF1, what will be the voltage it will induce? It will depend upon the magnetization curve of the core. So, therefore, it will be the voltage now with IF1. The voltage will be, let us say, E1. Okay. Okay. Now with E1, what will happen? Again, with the resistance line, again the current will become IF2. Okay. Then corresponding to IF2, again the voltage will increase to, let us say, E2. This is a dynamic phenomena, very quickly it achieves. We cannot see it, but I am explaining it through a figure. Now corresponding to E2, your current will be IF3. Okay. Now again corresponding to IF3, your voltage will become here E3. Okay. Okay, so like that it will go on increasing. If the saturation is not there, if it is a straight line, our magnetization curve, then the voltage will go on increasing. So this is how the saturation actually helps us to stabilize the voltage. Okay. Therefore, saturation is a boon for the shunt connected DC generators. Okay. And saturation is very important here in case of shunt connected generator, that it stabilizes the induced EMF. It will not go on increasing unlimitedly or infinite value, right? It will stop at certain point, like at this point it will saturate at V no load, right? Where it will saturate to the particular value, it will not further increase, right? Now the question is, if the field resistance will change its value, can it develop for all the field resistance? Of course, it can develop, this voltage will develop for the resistance line below this magnetization curve, right? Now if I'll plot a magnetization curve here at this point, resistance line above the magnetization curve, will it develop the voltage? Can you test it? For the resistance line which is above the magnetization curve, can it develop the voltage? It cannot develop. Therefore, the resistance line which is parallel to the magnetization curve is known as critical resistance of the field. Okay. So this critical resistance of field plays very important role. Therefore, we cannot add the resistance in the shunt field circuit as we wish. We cannot add it. Okay. So therefore, we can see here in this curve. So there are various resistance lines plotted here. RF1, RF, RF2, RC, right? And RC is the critical resistance line, because beyond this will not develop the voltage. Okay? I hope everybody understood this concept. Okay? Backside, any doubt? Okay. So now this is clear, right? Okay. So hence the voltage build-up will take place in a shunt generator if a residual flux exists. These are the conditions for which the shunt generator will produce an EMF. If these conditions are not satisfied, then it cannot produce the flux, cannot produce the EMF, right? So now the first condition is the residual flux must be there in the field circuit, field poles, right? Second point, the field winding MMA produces the flux that aids the residual flux. Suppose your residual flux is there and you have connected the field in such a way that now the current in the reverse direction, it will oppose the residual flux. So initially if it will oppose the residual flux, then what will happen? It cannot produce the field EMF, right? So therefore it must aid the residual flux, right? The third condition is the field circuit resistance is less than the critical resistance. It should be less than the critical resistance. If it will be greater than the critical resistance, then also it cannot produce EMF, right? So these three conditions you must remember, very important conditions, right? Okay. Now we are finished. Okay, one external characteristic we'll talk about. Up to this point it is clear to all of you, right? Now the external characteristic. As we plotted the external characteristic for the separately excited generator, here we'll plot the external characteristic for the shunt connected self-excited generator, right? So the same kind of curve will come, right? We can see here, this is the no load voltage line, right? If we'll plot the terminal voltage versus the load current, this is your first we'll write the equation. So equation is terminal voltage is equal to EA minus IARA, right? Okay, so based on this equation we can write this, right? Now your EA minus IARA, now EA will depend upon the flux phi P, right? And phi P is dependent upon the IF, and IF is equal to Vt upon RF. Okay, now considering these equations we'll plot the external characteristic, right? Now let us say so Vt will depend upon EA minus IARA, right? Now if your Vt will reduce, then it will impact the IF, field current, right? So then if it will further reduce, so as IF will reduce, let us say Vt is reduced, then it will lead to reduction in IF. If IF reduced, your phi P will reduce. Your phi P will reduce means EA will reduce. Then EA reduce means again Vt will reduce. Right? Again it will come to this. So this is a loop. And now if this will continue, this phenomena will continue, then what will happen? There is a voltage collapse. Suddenly it will become, the voltage across the terminal will become zero. Right? So therefore here also your saturation plays very important role. Because of the saturation only your voltage remains in a stable condition. Okay? So that saturation, that means that magnetization curve, saturated magnetization curve plays very important role here in order to stabilize, right? Here we can see this is the armature drop, right? And this is your drop because of the armature reaction. And when armature reaction drop happens, it will reduce Vt further, and as Vt will reduce, IF will reduce, then your field current will reduce, right? Again the voltage will, suddenly it will drop to zero at this point. So this phenomena will be stopped only when there is a saturation point in the magnetization curve. If the machine is operating in the saturation region, if the machine is operating in the linear region, then we cannot control the voltage, it will drop down suddenly, right? Drop down to zero. So therefore, we should remember this point that the shunt connected self-excited DC generator should be operated in the saturation zone. Okay, it should not be operated in the linear region, right? Okay. Now this is a problem, please do it.